Hi there. I'm Fernand Brunschwig again. I've got a special challenge for you. I'd like to show you a special effect of polarization and then show you how to calculate the actual result. The special effect I want to show you is with these Polaroid films. If we have two crossed Polaroid, like so, this is a sheet with two linear polarizers, and we cross them this way so that we are extinguishing all the light. And then the third sheet, if we put it in the middle, whoops, I turned off the light. If the third sheet, if we put it in the middle, if it is crossed with the top one, then all the light is extinguished in the middle. But if we turn it, it gradually transmits more light until at 45 degrees it's transmitting even more. And then if we go beyond the 45 degrees, it gradually decreases until it's crossed with the bottom sheet, and then you're not seeing anything there in the middle. So there's some kind of a mathematical function that we can use, that we can find, that will tell us the intensity of the light coming through as a function of that angle. So let's see if we can find out what that function's going to be. So we use the same technique we've used all along. We analyze the first filter, which is a filter that allows in only vertical light, and so coming out of it is all vertical light, a pure state. 50% of the light is going to be in that pure state. And then we put it into a filter that is going to be at a varying angle. And there's one axis. These are the two axes, and this is the formula for a rotating set of axes. If you make a drawing and plot it out carefully, you can find that the rotated axes have these trigonometric functions. So this is the transmitting axis, and this is the absorbing axis. And if we find the components of the vertically polarized light with the transmitting axis, we have to find the projection, the component of this light, of this vector, in this direction. And we can get that by the dot product. The dot product is 1 times the cosine, plus 0 times minus the sine, which is 0. So the result is the cosine. And then over here, the same kind of idea, we get the sine. And that is going to be light that is going to be light that is lined up with the transmission axis, so it will have a vector of the same form, and its intensity will be the square of this coefficient, cosine squared. Now we have light like that, and we're going to put that through a third filter. This third filter is oriented perpendicular to the first filter. As you can see, I have 0, 1, 1, 0. It is perpendicular to this filter, and we then have to look at the components of the incoming light in the directions of the filter axes. The filter is defining these two directions as the directions of the fundamental for analysis of the light, and so we just have to find the components of this vector in these directions, and we do that with the dot product as usual. Cosine times 0 plus minus sine times 1 gives us minus sine, and the same thing over here, and that will mean that the transmission, the light coming through, is horizontally polarized at an intensity of the square of this coefficient, sine squared. So the net effect of all of it is that we have 1/2 from the first filter, we have cosine squared